Gravitational time dilation is a form of time dilation. An actual difference of elapsed time between two events is measured by observers situated at varying distances from a gravitating mass. The weaker the gravitational potential, the faster time passes. Albert Einstein originally predicted this effect in his theory of relativity, and it has since been confirmed by tests of general relativity. This has been demonstrated by noting that atomic clocks at differing altitudes will eventually show different times. The effects detected in such Earth-bound experiments are extremely small, with differences being measured in nanoseconds. Demonstrating greater effects would require greater distances from the Earth or a larger gravitational source. In general relativity, it is considered to be a difference in the passage of proper time at different positions is described by a metric tensor of spacetime. The existence of gravitational time dilation was first confirmed directly by the Pound-Rebka experiment in 1959. Definition: clocks that are far from massive bodies run more quickly, and clocks close to massive bodies run more slowly. For example, considered over the total lifetime of the Earth, a clock set at the peak of Mount Everest would be about 39 hours ahead of a clock set at sea level. This is because gravitational time dilation is manifested in accelerated frames of reference, or, by virtue of the equivalence principle, in the gravitational field of massive objects. According to general relativity, inertial mass and gravitational mass are the same, and all accelerated reference frames are physically equivalent to a gravitational field of the same strength. Let us consider a family of observers along a straight, vertical line, each of whom experiences a constant g-force along this line. Let be the dependence a g-force on height, a coordinate along aforementioned line. The equation with respect to a base observer it is where is the total time dilation at a distant position, is the dependence a g-force on height, is the speed of light, and denotes exponentiation by e. For simplicity, in a Rindler's family of observers in a flat space-time, the dependence would be width constant, which yields. On the other hand, when is nearly constant and is much smaller than the linear, weak field approximation may also be used. See Ehrenfest paradox for application of the same formula to a rotating reference frame in flat space-time. Outside a non-rotating sphere, a common equation used to determine gravitational time dilation is derived from the Schwarzschild metric, which describes space-time in the vicinity of a non-rotating massive spherically symmetric object. The equation is: where is the proper time between events A and B for a slow-ticking observer within the gravitational field, is the coordinate time between events A and B for a fast-ticking observer at an arbitrarily large distance from the massive object, is the gravitational constant, is the mass of the object creating the gravitational field, is the radial coordinate of the observer, is the speed of light, and is the Schwarzschild radius. To illustrate then, without accounting for the effects of rotation, proximity to the Earth's gravitational well will cause a clock on the planet's surface to accumulate around 0.0219 fewer seconds over a period of 1 year than would a distant observer's clock. In comparison, a clock on the surface of the Sun will accumulate around 66.4 fewer seconds in 1 year. Circular orbits. In the Schwarzschild metric, free-falling objects can be in circular orbits if the orbital radius is larger than. The formula for a clock at rest is given above. For a clock in a circular orbit, the formula is instead. Important features of gravitational time dilation. According to the general theory of relativity, gravitational time dilation is co-present with the existence of an accelerated reference frame. Additionally, all physical phenomena in similar circumstances undergo time dilation equally according to the equivalence principle used in the general theory of relativity. The speed of light in a locale is always equal to c according to the observer who is there. That is, every infinitesimal region of space-time may be assigned its own proper time, and the speed of light according to the proper time at that region is always C. This is the case whether or not a given region is occupied by an observer. A time delay is measured for signals that bend near the Sun, headed towards Venus, and bounce back to Earth along a more or less similar path. There is no violation of the speed of light in the sense above, as any observer observing the speed of photons in their region find the speed of those photons to be c, while the speed that it takes light to travel the finite distance past the Sun will differ from c. If an observer is able to track the light in a remote, distant locale which intercepts a remote, time-dilated observer nearer to a more massive body, that first observer tracks that both the remote light and that remote time-dilated observer have a slower time clock than other light which is coming to the first observer at c. Like all other light, the first observer really can observe. If the other, remote light eventually intercepts the first observer, it too will be measured at c by the first observer. Time dilation in a gravitational field is equals time dilation in far space, due to a speed that is needed to escape that gravitational field. Here is the proof. 1. Time dilation inside a gravitational field g per this article is 2. Escape velocity from g is 3. Time dilation formula per general relativity is 4. Substituting escape velocity for v in the above proved by comparing 1 and 4. This should be true for any gravitational fields considering simple scenarios like non-rotation etc. Below is one evident example: a time stopped at surface of a black hole. B. Escape velocity from surface of a black hole is equal c. C. Time stopped at speed d equals c. Here asterisk is the proper time between events A and B for a slow-ticking observer within the gravitational field. Asterisk is the coordinate time between events A and B for a fast-ticking observer at an arbitrarily large distance from the massive object. Asterisk is the gravitational constant. Asterisk is the mass of the object creating the gravitational field. Asterisk is the radial coordinate of the observer, which is analogous to the classical distance from the center of the object. Asterisk is the speed of light. Asterisk is the velocity. Asterisk is gravitational acceleration. Field equals experimental confirmation. Gravitational time dilation has been experimentally measured using atomic clocks on airplanes. The clocks aboard the airplanes were slightly faster than clocks on the ground. The effect is significant enough that the Global Positioning System's artificial satellites need to have their clocks corrected. Additionally, time dilations due to height differences of less than 1 meter have been experimentally verified in the laboratory. Gravitational time dilation has also been confirmed by the Pound-Rebka experiment, observations of the spectra of the white dwarf Sirius B, and experiments with time signals sent to and from Viking 1 Mars lander.